Let's take a look at the couple of questions we had for homework on page 708 involving photons. Remember that Einstein said in 1905 that light exists as a particle as well as a wave. So not only do we have this wave nature, but we have this particle nature of light as well. This particle we call a photon, and this photon has an energy equal to h times f, or hc over lambda. So essentially we're saying now that there's a wave-particle duality. There's a wave nature of light as illustrated by polarization, illustrated by refraction, diffraction, interference. But there's also a particle nature of light. A particle nature of light that is described by this term, this new term that Einstein introduced called a photon, a quantum of energy, a particle of light. Again, the energy of that photon, of that quantum of energy, is equal to hf, or it's equal to hc over lambda. The value of h, it's a constant, but there's two values that we can use. 6.63 times 10 to the minus 34 joules seconds, or 4.14 times 10 to the minus 15 electron volt seconds. This one always works. This one we said sometimes works. In fact, most times it does. What I would suggest you do in terms of deciding which constant to use whichever one's convenient. Use the 6.63 or the 4.14, whichever one's convenient, unless you're sure that the second one, 4.14, is not valid. If it's not valid, then go to the first one, 6.63 times 10 to the minus 34. If you're not sure, like if you're just really not sure whether the second one is valid or not in a particular situation, then what should you do? Use the first one, because it always works. It just means sometimes a little bit of extra work for you, that's all. All right, let's take a look at the homework questions that we had on page 708 and see what we can do with those. Any issues with question number 1? Question number 2? Yeah, okay, let's take a look at number 2 then. It says, how many 400 nanometer blue light photons per second are required to deliver 10 watts of power? We've got a wavelength here in number 2 of 400 nanometers, or 400 times 10 to the minus 9 meters. We've got a power here of 10 watts. We're looking for the number of photons. Is there anything else we have if we read between the lines? How many photons per second do we have? That's 1 second. Let's say the time, if we're looking for the number of photons in 1 second, the time is going to be 1.00 seconds. You know from your electricity unit, when you were looking for the number of electrons, you used the total charge divided by the charge of one individual electron. You know that when you want to find a number of anything, you take the total something divided by the something for 1. When we want to find the number of photons, we're going to take the total energy and divide it by the energy for 1 photon. Now, the energy for 1 photon in this question is pretty easy to find. We can say E is equal to hc over lambda, 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 400 times 10 to the minus 9. What do we end up getting for that, by the way? Gives us 4.97 times 10 to the minus 19 joules. Now, if you did that in electron volts, use the 4.14 constant, that would be okay. But just understand if you do that, your answer is going to be the electron volts as well. And that's fine. The energy total. How do I find the total energy here in 1 second? Well, power is equal to work over time, or energy over time. Energy is equal to power times time. The power is 10 watts. The time is 1 second. So the energy ends up being the same as the power in this case. Why is the energy the same as the power? Because power is energy per second. So effectively what I'm given here, when I'm given the 10 watts of power, I'm given the energy in 1 second. And that's exactly what I want since I'm looking for the number of photons in 1 second. Now let's do the math there. 10 joules divided by 4.97 times 10 to the negative 15 joules. When we do that math, we get an answer that is 2.0 times 10 to the 19 joules. Is that okay? Sorry, 2.0 times 10 to the 19 photons, right? We can put photons per second if we want, or we can just leave it that way because it's a number. We don't have to have any units after it. that okay? It's not so bad, is it? Question number 2 is a tricky question, I think, but you know, we can expect to see questions of that difficulty for sure. They're not all going to be like that, but some of them will. All right, I'm not going to give you a chance to work on this right now unless we have a little bit of time at the end of class. You're going to have to do it for homework. But I'd like you to work on, for Monday, please, page 710, number 1 to 6. 710, number 1 to 6 for Monday. And as I say, if we have a little bit of time at the end of class, then we'll give you that time to work on these questions. But for now, we'll just hold off on that. So our demonstration showed us exactly what's going on with this photoelectric effect thing. The whole idea that light strikes a piece of metal, electrons are ejected sometimes. Discovered in 1887 by Heinrich Hertz, wasn't explained for another 18 years till 1905 by Albert Einstein. First time we've mentioned Einstein, I think, in Physics 30, isn't it? We're going to mention him several times now between now and the end of the year. Photoelectric effect is essentially light strikes a piece of metal. Sometimes electrons are ejected. Sometimes. Not all the time, but sometimes. Heinrich Hertz and people that followed him knew exactly when electrons would be ejected. They did experiments and they saw that visible light might not cause it, but ultraviolet might cause it, and so on and so on. But nobody knew why. This kind of light would cause it, and this kind of light wouldn't cause it, and whatever. So Heinrich Hertz suggests, oh, okay, this kind of light isn't causing electrons to be ejected. Let's jack up the intensity of that kind of light. Let's make it brighter light. That'll cause the electrons to be ejected, but it doesn't happen. If this kind of light doesn't cause the electrons to be ejected, then this kind of light will never cause the electrons to be ejected regardless of the intensity. What we need is not more light to cause the electrons to be ejected. If the electrons aren't being ejected, we need more energy. Hertz argued that that energy came from more light. Einstein argued that that energy came from higher frequency. Higher frequency light, higher energy light. That explained perfectly the observations that have been made between 1887 and 1905. The observations that said, look, if visible light doesn't cause it, maybe ultraviolet will. Why? Because ultraviolet is a higher frequency and therefore a higher energy than visible light. If visible light doesn't cause it, get more visible light, still won't cause it. More intense visible light still won't cause it because it's not a higher frequency and therefore it's not a higher energy. This infers that there is a minimum frequency necessary to eject electrons. Below that, nothing happens. Above that, something happens. That minimum frequency is called the threshold frequency, and it's given by the symbol F0. The minimum frequency necessary, the minimum frequency of EMR, necessary to eject electrons. Anything below that frequency, nothing happens. Doesn't matter how much of the light that we have. Anything above that frequency, something happens. Doesn't matter how little of that we have. Well, if there's a minimum frequency, there's therefore going to be a minimum energy as well. The minimum energy is called the work function. The work function is the minimum energy of EMR necessary to eject electrons. Final little thing here. If energy is h times F, then minimum energy, work function, is equal to h times, well, energy is hf. Minimum energy would be h times minimum frequency, or h times FO. So the work function equation, and it does appear on our data sheet, is h times the threshold frequency. Good? All right, finish copying that out. When you're done, you can pack it up and take off. Have a good weekend, everyone. We'll see you on Monday. Make sure you have those check and reflect questions done, please, for Monday.